The Elettra laboratory is located not very far from Trieste, on the Carso near the town of Basovizza. It was built to produce an exceptionally bright light, synchrotron radiation, a tool that enables researchers to detect structural details of materials otherwise invisible. This tool has many applications in different fields. Let's have a look at the source of this light with such exceptional features. Everything starts in the booster that shoots electrons and accelerates them at extremely high energy. An electron source is located in the first part of the booster. Here, charged particles are admitted by a metal electrode using a principle similar to that operating in the cathode ray tube of a standard television set. The electrons are guided inside a thin, circular, high-vacuum steel tube of 120 meters circumference through intense electromagnetic fields. They are then accelerated to 2.5 billion electron volt. The electrons are shot like cannonballs from the booster into the transfer line and finally injected into the storage ring, 260 meters long. Here they will circle for 24 hours without interruption, almost at the speed of light, and their energy will remain constant. During this time span, they will cover a distance equivalent to 4 times the diameter of the solar system. Synchrotron light is generated in the storage ring. The ring is, in fact, an alternation of straight and curved sections. In each curved section, a powerful magnet guides the electrons, forcing them to deviate from their path. Each time they deviate, the electrons emit energy in the form of light. The beams of light tangent to the storage ring are conveyed into the beam lines, where the experiments are performed. Today, Elettra has 23 operating beam lines, each specialized in a different field of measurement. This allows a broad variety of materials to be analyzed. The applications range widely from chemistry to biology, electronics, environmental science, materials engineering, medicine, nanotechnology, and archaeology. For example, the X-ray diffraction beamline allows us to study the structure of viruses and proteins by locating their atoms in space. Like all the other beamlines, the X-ray diffraction station includes various optical devices that select the needed wavelength and terminates with the experimental chamber where the sample is located. The light, in this case X-rays, interacts with the sample, for example a protein, in a particular way, according to the position of the atoms. This phenomenon is called diffraction. The diffracted X-rays form an image that can be seen by means of a detector. This image contains all the structural information of the sample. Using a particular software based on the principles of physics and mathematics, the researchers are then able to uncover the three-dimensional structure of the protein, atom by atom. One of the applications is the design of new drugs.